Gut. Könnt ihr nochmal sagen, dass ihr alle happy seid?
Ja.
Ja.
Ja, alle
Bin
happy.
happy.
Gut, weil sonst, ja, genau. Man kann sich, glaube ich, auch melden und genau, man kann auch Emoticons. Gut, dann fangen wir mal an. Und ich werde die Lehre auf Englisch machen, weil ich immer Lehre auf Englisch mache. Aber ich denke, das ist okay. So, good morning. Yeah, so the background here is that I was asked to talk about meta-analysis and the statistics of meta-analysis. And of course, meta-analysis is a big field, and the other problem, if you want, is that I actually don't have any experience with meta-analysis. I will talk a little bit about my background in the beginning and why I don't have experience with meta-analysis and what I in general think about meta-analysis. So I basically looked into some aspects of meta-analysis that I found interesting, in a way extending my previous reading of statistics for data science. So we have started a data science master here at Freie Universität Berlin, where I give the data science lecture and the statistics for data science lecture. And in this context, I now prepared some stuff on meta-analysis. So so what do I mean when I talk about meta-analysis? So obviously, and that's also you will be aware of that when we talk about meta-analysis, we primarily think about a set of quantitative methods for combining evidence. Usually it relies on data in the form of summary statistics as we find them in papers, so scientific reports, and hence meta-analysis. Actually, the one who's coughing, can you do me a favor and stop your microphone?
Yep, sure.
That's a little bit mean, but it's actually in the classroom we cannot do that, but virtually we can do it. Now nobody has their microphone on anymore, so I hope you're still there and I'm not talking to the void here. So meta-analysis is then the analysis of the results of statistical analysis. One thing before I continue, there should be something about raising your hand or something. Jasper, can you make yourself known? Sehr gut. Then
Hi.
hey, this is helpful. So because if you want to raise your hand at any point, do that. It seems to be possible. Jasper, can you briefly explain how you did it?
Just on the right side, there's a button, like next to rename, raise your hand. And then also if you don't want to raise your hand anymore, you can lower it if your question has been answered already or something.
Good. So please do that so that I am aware if there's something going on. So I try to monitor that here next to my slides. Good. So now a little bit more about how I came to speak about meta-analysis today. So like I said, I haven't done a meta-analysis before. So my background is in probabilistic modeling for frequentist and Bayesian inference. So originally I am trained in brain imaging, neuroimaging, cognitive neuroscience, and math, and in cognitive neuroscience and the analysis of neuroimaging data. Of course, we rely heavily on statistical inference, and both frequentist and Bayesian inference are quite prominent there. But of course, I'm mainly have looked into the neuroimaging statistical literature so far, and now with and also been teaching mostly in this kind of niche of neuroimaging statistics for some time, and now with our data science master have kind of broadened the scope of statistical teaching a little bit more. So I'm kind of looking at, if you're aware of classical frequentist statistics with Bayesian statistics, from my point of view, this is all just probabilistic modeling. And so I'm not kind of like a frequentist or Bayesian statistician, but I'm kind of view this whole thing as a probabilistic modeling approach. I've used that quite a lot in neuroimaging for neuroimaging data analysis and behavioral data analysis. And kind of my special topic in neuroimaging is variational inference for time series. That's because that's happening quite a lot in neuroimaging, and also for some time I was quite interested in the free energy principle. Can you raise your hand if you have heard about the free energy principle, people? So who has heard about free energy? Jasper knows how to raise his hand and has heard about the free energy principle. You can lower your hand, Jasper. That's awesome. Most of you haven't heard, but that's a variational inference. It's a modern technique. So in general, I work in computational cognitive neuroscience and data science. So that's where I'm coming from. So I'm not a meta-analysis expert by no means. So this is why I also asked Temel when he first asked me to talk about meta-analysis. I said maybe, so basically I don't know much about meta-analysis. Essentially, I did not know anything. So let's find someone else. We asked someone else, Fichtbauer, who's kind of a methods guy in meta-analysis, but he couldn't make it even before Corona. So then in the end, it came down to me, but I prepared something and maybe that's helpful. So before I go a little bit into talking about some statistics for meta-analysis, one thing that, where I don't know about meta-analysis too much, and also, or my viewpoint on meta-analysis maybe. So in general, I'm a proponent of open research, open science, and especially open methods. So I think that from all the studies that we do, the primary raw data should be available in standardized format. Of course, respecting, if it's human data, privacy protection laws. But within the scientific community, I think primary raw data should be shared. And hence, if we combine evidence from multiple studies, what we should combine are the raw data, and then maybe have big data sets because we have many participants. And from this point of view, I think actually the analysis of the results of analysis, so that you basically have a paper and you look up in a paper what they found, what their average score is, what their standard deviation is, it's kind of obsolete, because ideally you would just have access to the actual raw data. And then if you have, I'm interested in basically combining evidence over studies, you would have many raw data sets and could analyze them basically as if they would be your primary data sets that you acquired. So from my perspective, meta-analysis proper, so that you look into papers, write out the observed effect sizes, and then use some statistics to combine them, that should be obsolete. That's my opinion. And what would be interesting then, or what would be of main concern, would be multi-level modeling, so that you basically account for the fact that data were acquired in different studies, in different research centers, and maybe at different times and so on. So this is maybe not the main reason why I never really get into meta-analysis, but definitely one reason why why I'm not kind of the most meta-analytic guy. Another reason why I'm not the most meta-analytic guy is because I believe that especially young research, they really should get their hands dirty and do primary data acquisition and so on, so that they not only learn kind of the nice life on sitting on a computer and analyzing data, but they also learn what it means to acquire data. But that's a different point. Ja,
Just
sorry.
one.
Ja,
Kann ich auf Deutsch oder auf Englisch? Mir ist eigentlich egal.
auf Englisch.
Okay, so my question was actually for the multi-level modeling should be central. What do you think, who should do this? What do you mean with central? So everybody can do it on their own, or like there's like really like an organization doing that, or?
No, I mean it should be central to the academic or the scientific research endeavor. So I mean, everybody can do it, of course, but it should be central. So the focus should. So what I'm trying to say is the focus should not be on going through papers and figuring out what they wrote, but to have the data sets from many studies and then doing a multi-level analysis of these data sets. So not central in this meaning of centralized, but in the meaning of at the heart of meta-analysis should be multi-level modeling.
Okay, right.
Yeah. So maybe, so was it Katrin who works in a meta-analysis lab? Somebody of you works in a meta-analysis lab. Who is that? Katrin? Hello? Katrin?
I'm not working there yet, but I'm gonna start. And
Okay.
I've done I've done a meta-analysis in the same lab some years ago.
Okay. And what is because obviously I'm kind of the outsider here, so what is the view there? So do they rather look into papers and from papers collect effect sizes and then model them, or are they rather working on many primary data sets?
No, they usually go into papers and collect the analyzed data from the papers.
Okay.
So their focus is still on meta-analysis.
In the sense of,
which is also due to the fact that you don't get the primary data for many studies yet.
Yeah, which is a bad thing, but and it's
Yep.
Especially basically because of this Hoffman meta-analysis, which was basically that happened in 2010, and then I think the idea for your new meta-analysis was to basically, as far as I understood this Slack post by Felice, I think exactly. The idea was to basically look at the data essentially from 2010 to 2020, right, Felice?
No, because that wasn't a meta-analysis actually. It was just a systematic review, which is nice because then you have a selection of data you could use or of articles you could use. So no, there's no meta-analysis on that topic so far.
No, I mean, yes, I agree, but yeah, so the question would be, so the data that you want to look at for the meta-analysis that you are planning, when were these experiments done? So were they done like in the 90s, in the 2000s, or in the 2010s? So
all of that,
all of that, okay, because
I think with differing like methods, but yes.
No, because in general, I think just this is before we actually talk about also how to look into data from papers. I think you should really look for available data sets, and also if you now start your own research, make sure that your data sets are available, because it's kind of obsolete that we don't have enough storage capacity or whatever to save and share the raw data, or that people don't standardize their data so that data can be reused. So I mean, for the last 10 years, definitely this has been possible. And if people between 2010 and 2020 don't share their original data, then it's weird, I would say. Anyway, that's some general remarks I wanted definitely to make in the beginning. So we do quite some work, kind of public outreach work, if you want, in open research. So if you're interested in open science in general, who has heard the term open science? Please raise your hand. So we have one person, Jesper, few people. If you want to learn more about open science, open research, how to share data, how to standardize data and so on, we have a open science summer school that we do in the collaboration with Oxford. It's scheduled for September. It should happen in Berlin. So far, like the Olympics, we think it will actually happen. And if it's not happening as a Präsenzveranstaltung, it will happen virtually. So it will happen. Then we have some stuff going on at Freie Universität with our Open Science Working Group. And of course, everybody of you should know the Open Science Framework for sharing research data. So that's kind of my something I wanted to get off my chest, because meta-analysis, like looking into papers and looking for what people analyze, that feels really like 90s stuff, yeah, at least to me. So it should be the data is available, and we reanalyze data from previous studies, and maybe we use multi-level modeling. But I also appreciate that this kind of sharing data has not fully made its way through all parts of psychological science. And especially if you're new to it, you might think it's still normal not to share your primary data and not to standardize that and not to make your scripts available. But it's not. It always depends a little bit on where you work, but definitely make sure that you work in an open research environment, because all other research is obsolete.
May I ask a question?
Yes, of course.
Has anyone ever investigated how or to what extent the results diverge when you do meta-analysis on the one hand and do multi-level modeling on the raw data on the other hand?
Well, I think that's actually, I mean, we will look a little bit into actually the difference in what I want to show you. So in the first part, we want to look into standardized effect size estimation. And in the second part, we actually look into multi-level modeling. And they are just different models. So things should diverge a little bit, especially if you have small sample size that you base your stuff on. But again, I assume somebody will have looked into that a little bit, but again, then I'm the outsider in meta-analysis. So
I just thought that it might be more work if you actually do multi-level modeling on different primary data, because they've been collected in different ways and you'd have to find a way to summarize them still. And I find that might be easier if you look at the summary statistics. So I just thought that if the results from meta-analysis and multi-level modeling do not diverge that much, then it might still be reasonable to conduct a meta-analysis instead.
Sure. So I would call actually both meta-analysis, if you want. Or because it's again, you have data from multiple studies, but of course you have much more flexibility if you don't rely on summarized data, because as soon as you summarize data, some information is lost. So because you collapse multiple data points onto a single data point, even if you just compute an average. Even more so if you compute a standard deviation. So some information will be lost, and you use your flexibility. So I think there is always more information in the raw data point than in the summary statistics. Of course, if you don't change essentially what you do to the raw data points in your multi-level approach as compared to what you do when you first if you look into the summary statistics and then model those, then of course it will not matter. But you have more flexibility. That's what I want to say here. Okay, so from this background, I then looked at what your aim was as a group, and as I understood it, the aim was to conduct a meta-analysis on evaluative conditioning and contingency awareness. So I think, as Felice said, that's what she proposed, and I hope everybody agreed with that, and that was not only her idea. In any case, there was, what I found on Slack was this Hoffman evaluative conditioning in humans and meta-analysis. And then when the idea was that I speak about meta-analysis, I looked into that. So what they do, what I find interesting, and what I could reasonably prepare. And what I then found is one thing, namely that I also had in the back of my head about meta-analysis, namely standardized effect size estimation. And what they write is recommended by Lipsey and somebody else. We adjusted effect sizes for biases in small samples using the correction formula proposed by Hedges 1981. So the first thing that they do is actually they do some kind of a correction for when they do effect size estimation. And that's one thing that then motivated me to look into what that really means and what this correction formula by Hedges is. And that's the first thing that I want to and talk about today. Then continuing what they did for the overall analysis and all subsequent analysis, we chose the mixed effects models. I then realized that, of course, fixed, random, and mixed effects models that are, of course, prominent all over or happening all over statistics, of course, also in neuroimaging, which has a long history in talking about fixed and random effects models for neuroimaging data analysis. They are also being used in meta-analysis, and I will talk a little bit about this, mainly making the point that general linear model theory and variance component estimation are important everywhere. And then the last thing that struck me from this article by Hoffman, and something that I also strongly always believe, and this is another reason why I kept my hands out of meta-analysis so far, and likely will also do that, is one thing they wrote: we wanted to assess whether the present meta-analytic sample might have been affected by publication bias. And that's also one thing that I actually, from this open research perspective, have a relatively strong prior about. So if you work in research, specifically if you work with pure experimentalists, they are really about that it's significant, that you have significant results. If they have a significant result, they want to publish it and they send it to Nature. If this PhD student finds that the result is not significant, they rather not publish it at all. So I think, just from my personal growing up in the academic system, that there is a huge publication bias, definitely in cognitive neuroscience and in cognitive neuroimaging, which of course makes me worry about the literature, and then also makes me worry to some degree about meta-analysis, because if basically all the studies that are published report significant, interesting, spannende findings, then something can't be right, in my opinion, because you always know from working in the lab that some projects just don't find effects, but they then don't see the light of publication. So one thing that I want to hence look at what you can actually do in meta-analysis to account for that effect, and this is what I want to look at in this publication, selection effects model. So that would be then basically the outline. First talking about standardized effect size estimation. So essentially things like glass delta cones D, and how to correct for small sample biases, then fixed random and mixed effects models, and finally this publication selection effects model. If you look into the study by Hoffman, they basically used the whole arsenal, everything that you can find in the meta-analysis methods literature in their study. I think they do it very well. So I think they are really, they use everything that can be used, but to cover everything that they do, I think this in the depth that is, in my opinion, required to understand what's actually happening, that would be too much. So so there is, so I will focus on these three aspects. Good. So basically this presentation is based on mainly the original literature by Hedges, a little bit by Wichtbauer. If I don't, so I can't, it's a little bit hard to tell your statistical background. So has anyone looked at the statistics for data science? Please raise your hand if you looked at the statistics for data science lecture here. Okay, that's two. So somebody else. So Katrin, maybe because I think you have the most experience, is that roughly what you have done in statistics, or is it very different? Can you give us an impression?
I think it's roughly what I have done, but partly only because I've done mathematical statistics as well.
Okay. Yeah, it's definitely a mathematical statistics course, I would say. So, but it covers nevertheless the topics that are happening also in psychology statistics. In your Katrin, in your mathematical statistics, did you also do Bayesian inference?
No, but we did that in psychology.
Yeah, that's somehow also when I studied math, the statistics there is focusing still on frequentist. In any case, we will only need frequentist statistics today. So a little bit more background before we finish this introduction. So a lot of the stuff that I'm talking about is by this guy, so Larry Hedges. For some reason, he reminds me of Harvey Weinstein these days, but that's just weird. So he's a mathematician, and he has done a lot in the in meta-analysis methods, and I think his stuff is good. So when I looked into meta-analysis now quickly, I, for example, bought this, I think it's Borenstein book from 2010. So it's like in neuroimaging. There's the real stuff where you really find the answers on how these things work, and then there is people who are not really into it describing what things do roughly, where you just get confused. And I found, for example, this, I think it's Borenstein, it's a blue book. I found that a little bit confusing, but the original literature by Hedges is fairly clear. So I just wanted to give credit here because I'm just basically telling you his story here. Then, before we can really start, I need to briefly prime you on how I view statistics and probabilistic modeling. So I don't view statistics like as a set of rules or cookbook recipes that you apply, and then on the last page of your cookbook recipe it says, yeah, it's allowed if the data is normally distributed or something like that, which you often find in psychology. So from my perspective, and of course that's from a reasonable perspective, everything is model-based. So the question is, when you talk about a statistical technique, the question is always, what's the model that generates the data? Then how the parameters of the model can be estimated based on the data, and how this model then is evaluated. So for me, statistics and probabilistic modeling, which already has it in its name, is always model-based. You need to understand what the model is, and then you can, based on the model, create estimators or inference procedures. And yeah, ideally, you then go back to model formulation. One thing that you might wonder here, why the data is part of science, that's just because your receptive sheet essentially is part of the scientific method. So the data that you acquire, of course, is registered in some kind of machine, whether it's an MRI machine or it's a computer when you do behavioral testing. And of course, the data is just, it's not reality itself, it's how reality is filtered by your data acquisition machine. Yeah. Just this is basically just to warn you that we will see quite some model formulation in when we look at the techniques. And then finally, the basic logic of frequentist inference, because the meta-analysis techniques that we will look at today, they are frequentist statistics based. So when we talk about computational modeling some other day, we will look at Bayesian inference, but here we look at frequentist inference, which always works as follows, which will also be implicit in the stuff that is happening later. So it's always assumed that out there in the world, there is a true but unknown parameter value in some parameter space. So this true but unknown parameter value here is this small theta in this parameter space, big theta. And then in frequentist inference, you can do a couple of things. One thing is to do a point estimation, where you basically give a very precise estimate, but are also most likely wrong. So for example, if your true but unknown parameter, let's say your true but unknown effect size is 2, then you can point estimate that, for example, by 2.3 or something. So you have a number by which you estimate that. And actually today we will only looking at point estimates. The other two things that you find in frequentist inference are confidence interval estimates, where you try to come up with coverage probabilities for your true but unknown parameter. And basically in this case, are a little bit less precise in your estimate of the parameter, but allow for a little bit more, just turned red. How did that happen? But allow for, so you're a little bit less precise, but allow for only some probability to be correct. And then the kind of the worst way of doing inference, if you want, is to do hypothesis testing, where you just partition the parameter space into two subsets and then just say, okay, the parameter is in this, the true but unknown parameter is in this part of the parameter space or in the other. So for example, it's 0 or it's not 0. So from an inference perspective, this is, you have a very high chance to be correct, but you're also fairly imprecise. Yeah, so we are mainly interested in this kind of setting here, that we do point estimates today. So it will be mainly about point estimation, but always keep in mind that what we have in our statistical analysis is just an estimate of the true but unknown parameter value, and the true but unknown parameter value we will never know. Good. Yeah, so that was the intro. Questions about the intro? No. Good. My suggestion would be that we take a break now. Can you raise your hand, or can you put on your audio, please? So
Hello.
Hello. I would suggest to take a break now, because I need breaks. Otherwise, at one point, I will be just trying to get my thing back here. Where am I? Sorry. I'm just trying to figure out where I am. Okay. So it's 10 o'clock now. I would suggest we have like a 15 minutes break now, and then start with standardized effect size estimation. Yeah?
Sounds
Oh.
good.
Okay.
Okay,
That's good.
so I will also put, I think, my micro on silent in the meantime, so don't worry. I will be back in 15 minutes. Yeah?
All right. See you.
Have a
Then.
good